welcome to this lecture number 37 of our course on fundamentals of transport processes. We were looking at fluid mechanics, and in the last lecture we had a little bit more to do in vorticity dynamics. Okay. If you recall, we previously did boundary layer theory, where we looked at the effect of viscosity in thin layers close to solid boundaries, and how that could in some instances result in separation of the boundary layer from the object and the formation of a wake behind the object. Previously, when we did potential flows, we consider the flows to be inviscid and irrotational. Irrotational means that the vorticity is equal to 0. I did not really justify that, the reason for doing that approximation at that stage, apart from the obvious rationale that if the curl of the velocity is equal to 0, then the velocity can be expressed as the gradient of a potential, and that greatly simplifies the formulation of the equations. In the last lecture, we looked at the effects of vorticity in an inviscid or a viscous fluid. Okay. The vorticity is defined as the curl of the velocity, okay, or in our notation, omega I is equal to epsilon I j k partial u k by partial x j, del cross u. Okay. And I showed you that the momentum conservation equation, Navier-Stokes momentum conservation equation, can be written partly in terms of the vorticity, okay, partial ui by partial t plus partial by partial xj xi. Half uj square minus epsilon I j k uj omega k is equal to minus partial p by partial xi. Okay. I should have a 1 over density there to make it the correct dimension, since I am dividing throughout by density. And there was a negative sign here, minus partial by partial xj of omega k. Okay, so del square u, the Laplacian of the velocity in the viscous term, can be written as minus of the curl of the vorticity. Okay. And in the last class, we also derived an equation, a balance equation for the vorticity, by just taking the curl of the entire momentum equation. Okay. That vorticity balance equation turned out to be partial omega I by partial t plus that was the balance equation for the vorticity. The entire left hand side in that equation, okay, the entire left hand side that I had in that equation was just the substantial derivative. Okay. And on the right hand side, I have two terms. The second term here is, of course, the usual viscous diffusion, nu del square, the kinematic. So, the diffusivity in this case is the same, it is the kinematic viscosity of the fluid. And then I have this additional term here, which had no analog in my momentum conservation equation. Okay, so, this acts as some kind of a source of vorticity. Okay. It increases. So, if I had an inviscid fluid, this viscous diffusion would be identically equal to 0, and the rate of change of vorticity is just equal to omega dot grad u. Okay. This first term here, omega j partial ui by partial xj. Okay. This we had derived in the last lecture, and I had given you a physical interpretation of this. Okay. The physical interpretation of this was, if I had, okay, if I had within a fluid flow field some line segment delta x vector, okay, if I had some line segment delta x vector, okay, and this is a material line segment, that is, it is moving along with the fluid. Okay, it is moving with the same velocity as the fluid at each point within this line segment. Okay. So, at some later time, this is going to move a distance u delta t, okay, where u is the velocity at the location x. Okay. So, this I can write this as delta t times u of x. Okay. This moves some other distance, okay, delta t times u of x plus delta x. Okay. So, the displacement at the time x plus t plus delta t is going to be this new one, which is final position minus the initial position, delta t into u at x plus delta x minus u at x, okay, which is basically equal to grad u, I am sorry, delta x dotted with grad u. Okay. U at x plus delta x minus u at x can be written as delta x times grad u. Okay. So, therefore, you have the rate of change of this delta x vector, the rate of change of delta x vector, because this is a material element that is moving with the fluid. At time t, you have a certain length delta x vector. At some other time t plus delta t, you have some other length delta x vector. The difference between the initial and the final positions basically gives you the rate at which delta x is changing with time. Okay. And as I told you, that can be written as delta x dot grad u. Okay. Note that d by dt is the substantial derivative. It is in a reference frame that is moving with the fluid, because I am considering this as a fluid material line element. That is being deformed because the fluid is flowing. If the velocity were a constant everywhere, then there would be no deformation, because both the ends of this vector are moving with exactly the same velocity. Therefore, they have exactly the same displacement, and there is no change in the length of that line segment. However, if the line segment, if the fluid velocity varies with position, then there is a change in that line segment. Okay. Written in vector notation, d delta x I by dt is equal to delta x j partial by partial x j of u I. Okay, that is written in vector notation, delta x dot grad u. The dot product is between delta x and the gradient. Note that this has exactly the same structure as this one. This has exactly the same structure as these two put together. D omega I by dt is equal to omega j times partial u I by partial x j. Therefore, vorticity increases, okay, or intensifies in the flow in a manner similar to material line elements in the flow. Okay. So, this is the mechanism for intensification of vorticity due to stretching or bending of vortex lines. As I had explained in the last lecture, in case when there is a two-dimensional flow, let us say the velocity is in the xy plane and it varies also in the xy plane, so that the flow is only in two dimensions, x and y. Okay. So, I have some velocity vector in this xy plane. Vorticity is the curl of the velocity. So, vorticity, since it is the curl of the velocity, it is perpendicular to this xy plane. So, therefore, the only non-zero component of the vorticity is going to be omega z, because the velocity is in the xy plane, the gradients are in the xy plane. Vorticity is the curl of the velocity. It is perpendicular both to the velocity direction and to the gradient direction. Therefore, vorticity is only in the z direction, and in that case this term will be identically equal to 0. So, there is no intensification of vorticity due to stretching or bending of vortex lines in two-dimensional flows. It exists only in three-dimensional flows. And associated with this mechanism, we had actually proved a theorem which was first due to Kelvin, okay, which basically states that for material line, okay, for some material loop, okay, I will call it as C, a closed loop. This is a closed loop C. This is a material closed loop. That means that every point on that loop moves with exactly the same velocity as the fluid at that particular point. So, at some later time, this loop will move to some other location. Okay. The circulation on this loop is given by gamma is equal to integral dx dot u over this closed loop C. Okay. And I had shown you that this, the rate of change of circulation that is the rate of change of circulation on this moving loop of fluid, material loop of fluid that is moving, okay, with the same velocity as the fluid velocity at that location. Okay. This can be written as the kinematic viscosity times integral, okay, of dx. Let me write this in indicial notation that makes it easier. So, this is what we had derived in the previous section, in the previous lecture, okay. And this can also be written as minus nu integral dxi epsilon I j k partial by partial x j of omega k. Okay. So, if you have an inviscid fluid in which the kinematic viscosity is equal to 0, then d gamma by dt is identically equal to 0. That means that the motion of the in a moving reference frame moving with that loop of fluid. Of course, the length of that loop could change in general, okay. But in a reference frame that is moving with that loop of fluid, there is no change in the vorticity, okay, on this. So, vorticity is convected unchanged through the fluid. That is one reason why we could have talked about potential flows, because you cannot generate vorticity within the flow. Vorticity is transported unchanged through the fluid, and the intensification of vorticity is similar to the intensification of material elements. So, if I had a fluid which was initially irrotational and there was no kinematic viscosity, at later times it has got to continue to be irrotational. There cannot be a source of vorticity within the flow itself. And that is the reason why we could talk about potential flows, because we know that if the flow initially did not have vorticity, it has to continue to not have vorticity internally, right. You cannot generate vorticity within the flow. So, where then can vorticity be generated? The answer is vorticity is generated at solid surfaces, okay. And vorticity that is generated at the solid surfaces is then convected unchanged through the flow. The only mechanism of intensification is this mechanism of stretching and bending of vortex lines, okay. And of course, there is a mechanism by which vorticity is reduced, the vorticity diffusion mechanism. The rate of change of vorticity also has a diffusive term there, which tends to attenuate, to damp out vorticity variations. So, let us look at how vorticity is generated at surfaces. Okay. If I have a surface here, okay, if I have a surface, let us call it x, okay. Let us call this y, call this z. Okay. We know that the shear stress at the wall tau x y is equal to mu partial u x by partial y. Okay. Now, because of the no slip condition at this wall, okay, because of the no slip condition at this wall, I know that at the surface itself u x has to be equal to 0, u y has to be equal to 0. There is a no normal velocity boundary condition, okay. And of course, in the third direction u z also has to be equal to 0 if there is a no slip condition at the wall. Okay. u y is equal to 0 implies, right, u y is equal to 0, right, at all values of x. U y is equal to 0 at all values of x implies that partial u y by partial x, this is also equal to 0, okay, because dy is equal to 0 at every location. Therefore, partial uy by partial is also equal to 0. Okay. So, therefore, for this surface I can write this as partial ux by partial y minus partial uy by partial x, because we know that partial uy by partial x is equal to 0 at the wall. This of course is equal to minus mu times omega z, because you know that omega z is equal to partial uy by partial x minus partial ux by partial y. Therefore, the shear stress is equal to the z component of the vorticity divided by the viscosity at the wall itself. The shear stress can be expressed explicitly in terms of the vorticity. Okay. So, this basically tells you that the value of the vorticity itself at the wall is exactly fixed by the shear stress. Okay. The force exerted at the surface, okay, the unit normal is in the y direction. Therefore, the force exerted in the x direction, the tangential force exerted in the x direction at the surface is equal to tau x y n y, okay, is equal to minus mu n y times u z. Okay. This is the viscous shear stress tangential to the surface. This can be generalized. In this particular case, I have taken a coordinate system with my x axis along the surface and my y axis perpendicular to the surface, but I can write this in a most general coordinate system as f vector is equal to minus mu n cross omega. Okay. So, this works regardless of which orientation the surface is in the coordinate system. Okay. You can see that this should be omega z. Okay. So, this basically tells us this f vector is the viscous force. This basically tells us that the value of the vorticity at the surface itself is equal to, okay, the viscous force divided by the viscosity, the tangential viscous force divided by the viscosity. So, this is like at the surface itself, the vorticity has a fixed value that is determined by the shear stress that is exerted at the surface. Okay. Similar to, for example, if I were doing a heat transfer problem, I would be able to fix the temperature at the surface. Okay. The temperature would have a finite value at the surface, and that it would change as you go within the fluid in agreement with the conservation equation, which contains the convective and the diffusive term. Similarly, in this case, the vorticity has a specific value at the surface, and of course, it varies as you go into the flow depending upon the convective, the viscous, and we have this additional vorticity intensification term. Okay. So, in accordance with these three terms, the vorticity would vary as you go within the fluid. However, in order to find out how much vorticity there is in the flow, it is not sufficient to know what the vorticity at the surface is. You have to know what is the flux of vorticity. Okay. What is the flux of vorticity that is taking place in the direction perpendicular to the flow. Okay. In the conservation equation, if you recall, for the vorticity, we had a diffusion term. In that diffusion term, the diffusion coefficient was identical to the kinematic viscosity of the fluid itself. Okay. Recall this diffusion term here. Okay. This diffusion term, okay, the diffusion coefficient is identical to the kinematic viscosity of the fluid itself. Okay. Therefore, the flux, okay, the flux of vorticity, okay, the flux of vorticity can be written in a manner similar. Okay, let me write this as the flux of vorticity. The flux of vorticity, okay, can be written in a manner similar to the flux of heat, for example, as minus nu times the n dot grad omega. Okay. So, in this particular case, where I have a surface with x and y coordinate, okay, the flux of vorticity in the y direction is equal to minus nu times n y, this equal to, okay, partial omega z by partial y. Okay. So, this is the vorticity that is coming out of the surface, the flux, the amount of vorticity coming out, okay, per unit area, per unit time into the fluid. Okay. So, that is the vorticity flux that is taking place, okay, from the surface. Turns out you can write an expression for this vorticity flux from the momentum conservation equation, which was expressed in terms of the vorticity itself. Okay. If you recall, the momentum conservation equation as expressed in terms of the vorticity is partial ui by partial t plus partial by partial xi of half rho ui square minus rho epsilon I j k u j omega k is equal to minus partial p by partial xi plus minus mu epsilon I j k partial by partial x j of omega k. Okay. You recall we had written the Laplacian of the velocity vector in terms of the vorticity here. Okay. And similarly, we had simplified these convective terms in terms of the vorticity. Okay. If you apply this equation at the surface itself, we have a no slip condition at the surface. Okay. We have a no slip condition at the surface. Okay. And therefore, all of these terms, all terms proportional to the velocity will go to 0. Okay. The first term goes to 0 because if the flow is at steady state is identically equal to 0. The next two terms, this term goes to 0 because the velocity is equal to 0 at the surface, this no slip condition. And if we are looking at the variation in the vorticity in the x momentum conservation equation, this term is also equal to 0 because I know that the velocity is equal to 0. Therefore, the gradient of velocity along the flow direction is equal to 0. Okay. So, for this particular case, you find that the equation becomes partial p by partial xi is equal to epsilon I j k mu partial omega k by partial x j, okay, with the negative sign. Okay. And if you simplify for this particular configuration x, y and z, where the vorticity is the only non-zero component of the vorticity is omega z. Okay. The only non-zero component of the vorticity is omega z because the flow is in the x y plane. Okay. The flow is in the x y plane, the only non-zero component of the vorticity is omega z. In that case, you will get partial p by partial x is equal to minus mu partial omega z by partial y. Okay. Because x is I and therefore, partial omega k by partial x I j will basically give you partial omega z by partial y, okay, which this is equal to minus, okay, mu by nu times j z omega as I have defined it. Okay. Sorry, this is j y omega. Okay. From this equation. Okay. So, this from this equation j y omega is equal to minus nu partial omega z by partial y. Okay. Therefore, this is equal to plus mu by nu times j y omega. Okay. So, this is just equal to rho times j omega y. So, this implies that the vorticity flux coming from the surface depends upon the pressure gradient at the surface. Okay. Only when there is a pressure gradient will you get a flux of vorticity coming out of the surface. Okay. If there is no pressure gradient, there will be no vorticity flux. Okay. So, therefore, for a flow where there is a pressure gradient along the surface, the vorticity flux is just equal to minus 1 is just equal to 1 over rho times the pressure gradient. Okay. The net vorticity flux between two locations here, okay, integral, okay, over dx of j y omega, okay, integral over the length. Okay. As you recall, when we did boundary layer theory, we integrated the force over the length. In order to find out how much vorticity is actually coming out of the surface, we can integrate the vorticity flux over the length. Note that this vorticity flux can be positive or negative depending upon whether the pressure gradient is positive or negative. Okay. It is negative if the pressure is decreasing downstream and it is positive if the pressure is increasing downstream. Okay. So, the net vorticity flux that is coming out, okay, integral, okay, dx jy omega from, okay, between two locations, let us call it as 0 and L, the start and the end of the surface. This is equal to integral, okay, between 0 to L dx of 1 by rho partial p by partial x, okay, which is equal to 1 by rho into p at x is equal to L minus p at x is equal to 0. So, the net amount of vorticity coming out from this stretch of surface, of course, this is a two-dimensional flow. So, the vorticity flux is defined only per unit area perpendicular to the plane of the board, okay. But per unit length perpendicular to the plane of the board, the total amount of vorticity coming out of the surface is proportional to the difference in pressure between the two ends of the surface. So, only in the case where you have a pressure driven flow where there is a pressure difference between the two ends will you have a net vorticity flux coming out of the surface, a net amount of vorticity. If the pressure at the two ends is the same, even though there may be pressure gradients in between, okay, if the pressure at the two ends is the same, the net amount of vorticity that is coming out has to be equal to 0. Even though at certain locations you may have vorticity coming out and other locations it goes back in, okay, such that the net vorticity is equal to 0. Okay. Our familiar example of cylinders or airplane wings, okay, if we solve the potential flow problem for a cylinder and we also motivated the potential flow problem for an airplane wing. Okay. As the fluid goes around this, okay, as the fluid goes around this, okay, if you look at the top surface alone, as the fluid is going around the surface, initially the streamlines are being compressed, okay, and then they expand again, okay, because the flow is being compressed above and below. So, initially the streamlines are being compressed and then they expand again. For this case, initially the velocity increases, you have an accelerating flow, then the velocity decreases again, you have a decelerating flow. Okay. When the flow accelerates, the pressure of course decreases because P is equal to minus half rho u square plus P naught. The pressure initially decreases and then as the flow decelerates, the pressure increases again. However, you know that the pressure at these two ends has to be the same because both ends are open to the atmosphere. So, the pressure at the two ends has to be the same. What that implies is for this particular case, the net amount of vorticity that is generated from the surface is going to be equal to 0, okay, because the pressure on the two ends has to be the same. Therefore, if you have even if you have a boundary layer, as long as that boundary layer is a confined boundary layer, the pressure at the two ends is exactly the same, and for that reason there will be no net vorticity generation from the surface. That is not true for a bluff body. Okay. For this bluff body, we found that what actually happens is that you have the flow accelerating as it goes around the cylinder on the upstream side. On the downstream side, there is one location at which the separation takes place. If you recall, that is where the parameter beta, that is the analogous parameter for the flow in a corner, goes below minus 0.0904. Okay. This is true for a cylinder and this is true for a sphere as well. Okay. So, in the accelerating region, if I plot the, okay, as a function of this angle theta, if I plot the pressure, okay, if I plot the pressure as a function of this angle theta around the surface, okay, at theta is equal to 0, you have the upstream edge. Okay. Upstream edge, the velocity, there is a stagnation point there, the velocity is very small. Okay. Therefore, I have the pressure is largest at this point, P as a function of theta. Theta goes from 0 to pi. Okay. Just by symmetry, okay, for the potential flow solution alone, okay, if I had the potential flow solution alone, okay, the potential flow solution actually goes all the way around. Okay. And I showed you just by symmetry that for the potential flow solution, there is a symmetry between the upstream and the downstream side. The pressure is equal to minus half u square minus rho u dot capital U, and because of that there is a symmetry between the upstream and the downstream side. That means that the pressure has to be large on both sides because the velocity is 0 at the stagnation points, and it comes down in between. Okay. Okay. It comes down in a symmetric manner in between. This axis of symmetry corresponds to pi by 2, which is the top and the bottom of the cylinder. Okay. This is what the potential flow solution predicts. But because of boundary layer separation, I showed you that there is actually a wake region that forms behind the cylinder. Okay. In this wake region, the pressure is actually much lower. Okay. And so, if you plot the pressure difference along with boundary layer separation, what you find is that it approximates the potential flow solution on the upstream side, because the boundary layer is attached to the surface. On the downstream side, at some point there is separation, and the pressure never recovers back to the original value that it had on the upstream side. So, if you plot the pressure going around the cylinder, you find that it decreases as in potential flow on the upstream side, but it does not recover back to the original pressure predicted by potential flow on the downstream side. So, between the upstream and the downstream stagnation points, there is this pressure difference. Okay. And because there is a pressure difference over the entire surface, there has to be a net vorticity that is generated. That vorticity effectively is what is generating the circulating flow in the wake behind, okay, even at high Reynolds number. Okay. So, this completes our discussion of vorticity dynamics. Vorticity cannot be created or destroyed within the flow. It can be attenuated if viscous effects are included, but if you neglect viscous effects, vorticity is convected without there can be no creation within the flow itself. It is generated at solid surfaces, and it is convected, and it's amplified by stretching or bending of vortex lines within the flow. Okay. And the net amount of generation of vorticity at a surface depends only upon, or the net flux at the surface depends only upon the difference in pressure between the two edges of the surface. So, this leads us naturally to our next topic, and that is turbulence. That is the flow in the wake of these objects, or the flow in pipes after transition takes place. It is a highly chaotic flow. Okay. It is called turbulent flow, and turbulence is a difficult topic, simply because the flow is so irregular. Okay. But first, what happens? How is turbulence generated? Okay. For example, for internal flows, okay, for a flow in a pipe, okay, we have solved the velocity profile on various occasions. Okay. We know that the fully developed laminar flow in a pipe is a parabolic velocity profile. Okay. However, as you keep increasing the Reynolds number, okay, at some point there is a spontaneous transition to what is called a turbulent flow. Okay. The turbulent flow, the velocity profile is much flatter. Okay. The velocity profile, it's more plug-like. Okay. For the same average velocity, the maximum velocity is lower. Okay. So, it's more plug-like velocity profile. Okay. Whereas in a laminar flow, you have nice straight streamlines. Okay. Okay. And the transport of momentum across the flow takes place only due to molecular diffusion. In this case, you have highly irregular streamlines, and you have velocities in all three directions, velocity fluctuations in all three directions at any instant in time, at any location. Okay. So, the velocities, even though the mean flow takes place only in one direction, the local fluid velocity is in general three dimensional. Okay. It has fluctuations in all directions, and fluctuations, there are parcels of fluid called eddies, okay, which have velocities in all directions, and there are eddies of various sizes within the flow. And this is reflected in, for example, in flow through pipes and channels. Okay. For the specific case of the flow through a pipe, if we plot the log of the friction factor versus the log of the Reynolds number, we know that the laminar profile satisfies a log law of the form F is equal to 16 by Re. At a Reynolds number corresponding to about 2100, there is a spontaneous transition that takes place to a turbulent flow with a much higher friction factor than what you would expect for a laminar flow. That is, the friction factor is much higher than 16 by RE. Therefore, this flow is much more dissipative, okay, than the 16 by RE law predicts. So, this happens for external flows as well. For example, the boundary layer flow. We got the velocity profile for a laminar boundary layer, the Blasius profile for a laminar boundary layer. Okay. At some point, this boundary layer itself will become unstable. Okay. The point is when the Reynolds number based upon x is equal to 5 into 10 power 5. About 500,000, when the Reynolds number reaches about 500,000, the boundary layer profile itself becomes unstable. It is no longer laminar, and you go on to what is called a turbulent boundary layer, which follows a different law for the boundary layer thickness as a function of Reynolds number, okay, and it is much more dissipative. In all of these cases, it is not that the laminar profile is no longer a solution of the equations. A similar thing happens, for example, in when you heat a fluid from below, there is an instability because of the density gradient. Similarly, in the case of rotating fluids, you find an instability which leads to eventually to turbulence. In all of these cases, it is not that the laminar velocity profile is no longer a solution. Okay. If you insert the laminar velocity profile into the Navier-Stokes equations, the equations are satisfied at all Reynolds numbers. Okay. For example, the parabolic flow in a pipe, that parabolic velocity profile satisfies the Navier-Stokes equations at all Reynolds numbers. So, the parabolic profile is still a solution of the equation, except that it is not a stable solution. Okay. So, the reason there is a transition is because the laminar profile goes unstable. It is still a solution of the equations, but any small disturbance will make it go to some other solution. Okay. To draw an analogy, okay, if I had a ball in a cup, okay, in a gravitational field, this is a stable configuration, because if I displace this cup a little bit, okay, if I displace this ball a little bit either on the left or on the right, or if there is an axisymmetric cup, I can displace it in any direction. This will just come back to its original state, because gravity is acting downwards. If I turn this upside down and I place the same thing over here, okay, at this point exactly all forces are balanced. So, this is a solution of the equations of motion for this particular case. It is a valid solution. The problem is, if I put a small disturbance in either direction, this will not come back. Okay. It will continue to go. Okay. It will continue to go until it reaches some other solution. Okay. So, the same thing for the flow transition in the flows in channels and pipes. The laminar solution is a stable solution at low Reynolds at all Reynolds numbers. The problem is, when the Reynolds number increases beyond a certain value, any spontaneous disturbance will make the flow go to a turbulent state. Okay. This brings us to an important point here, okay, and that is that if you recall, in the limit of low Reynolds number, okay, we had said that we neglect the inertial terms, and because of that the equations end up being linear. That means that the solutions exist and they are unique. Okay. So, for low Reynolds number you can have only one particular solution. Okay. However, in the high Reynolds number limit, the inertial terms become important, and therefore, the solution is no longer unique. Because the solution is no longer unique, there could be multiple solutions for the Navier-Stokes mass and momentum conservation equations for a specific configuration. Laminar solution still exists. The problem is that if I have a flow in a pipe with a laminar flow, parabolic velocity profile, and I put a small disturbance anywhere, right, just I put a small disturbance for this particular case, the solution goes to some other solution, and that other solution is the turbulent flow. Okay. So, the first thing, okay, turbulence. First thing, it is a high Reynolds number phenomenon. The first thing is the high Reynolds number phenomenon, because we know at low Reynolds number equations become linear and the solutions are unique. Okay. So, you require high Reynolds number for in order to have a turbulent flow. Okay. So, it is a phenomenon of high Reynolds number. The second important point is that it is a continuum phenomenon. It is obtained by a solution of the continuum equations, that is the continuum Navier-Stokes equations. It is not that the continuum approximation itself breaks down. Okay. So, it is a continuum phenomenon. Even though there are large fluctuations in a turbulent flow, it is still a continuum phenomenon. Okay. The third thing is that it is highly irregular. Okay. As I said, the velocity profile in a turbulent flow looks more plug like. Okay. It is not parabolic, okay, whereas it is flatter than a parabola at the center, and it has a sharper gradient at the walls. Okay. That is only the mean velocity profile if I average the velocity over a long period of time. Okay. The local velocity profile actually has fluctuations of various length scales, okay, called eddies, in various directions. At any given point in time, if I were to plot any component of the velocity, okay, so for example, if I were to sit at one particular location, and plot as a function of time, okay, the velocity component u x, say. Okay, so, let us put our coordinate system here. X is the flow direction, okay, and y and z are the gradient, are the two directions perpendicular to the direction of flow. Y is the direction of the gradient, the direction in which the mean velocity varies. If I were to sit at one particular location and I were to plot the velocity u x, of course, it has an average value, okay, the mean value at that location. Okay. This is the mean value at that location. Okay. However, if you plot the instantaneous velocity, you will find that it actually fluctuates. Okay. It fluctuates around the mean. Okay. It has a highly irregular fluctuations about the mean. Okay. So, there is u x. Okay. In addition, you will find that there are velocity fluctuations both in the y and the z directions as well. It is not that you just have fluctuations in the x direction alone, you have fluctuations both in the y and the z directions as well. Okay. So, the y velocity will also fluctuate, okay, even though the mean y velocity is equal to 0, okay, and you will have fluctuations in the z velocity as well. Okay. So, it is a highly irregular flow with fluctuations in all three directions at each point in space. Okay. And as I said, the fluctuations are three dimensional. You cannot have two dimensional turbulence. Even though the mean velocity profile may be only two dimensional, the fluctuations in general occur in all three directions. Okay. The reason is a little complicated, but it has got to do with the fact that an important step in turbulent energy transfer through to these fluctuations is the intensification of vorticity due to the stretching and bending of vortex lines. If you recall, when we did vorticity dynamics, I told you that vorticity of course diffuses by a mechanism similar to viscous diffusion. However, it is also stretched and bent due to the intensification, it is also intensified due to the stretching and bending of vortex lines in a manner similar to the change in material line elements due to the gradient in the velocity. That mechanism, if you recall, I had said that it does it in two dimensions, that is identically equal to 0, because I have a two dimensional velocity profile with two components u x and u y varying in the x and y directions. the vorticity vector is perpendicular to both of these. So, it is in the z direction, and because of that, that mechanism is absent in 2 dimensions, because I have omega z and the strain rate is in the x and y plane. So, in that particular case it is equal to 0. Therefore, you need to have a 3-dimensional flow in order to be able to intensify vorticity by stretching and bending of vortex lines. That means that turbulence has to be 3-dimensional. Okay. In addition, it is highly diffusive. The diffusion coefficient in a turbulent flow are often orders of magnitude larger than that in a laminar flow. Okay. The reason for that is because this mixing that is taking place due to the transport by these eddies, these parcels of fluid. Okay. Formally, an eddy is defined as a parcel of fluid in correlated motion. Okay. These little packets of fluid, as I said, they have velocities in all 3 directions. So, they are moving both streamwise and cross stream. And an eddy that moves in the cross stream direction will take along its temperature for large distances in the cross stream direction. In a laminar flow, this diffusion occurs due to molecular diffusion, due to the transport of molecules across a surface, okay, which results in mixing. And that diffusion coefficient, if you recall, in a gas is the same whether it is for heat, mass or momentum transfer, because the mechanism is the same. It takes place by the actual motion of molecules. Okay. And this mechanism, this transport scales roughly as the mean free path times the fluctuating velocity. The fluctuating velocity in a gas is equal to the square root of kT by m. Okay. Half mv square for the molecules, the molecular velocity fluctuations, half mv square is equal to 3 by 2 kT. Therefore, the velocity scales as kT by m power half. That velocity times the length scale, the mean free path, is what constitutes the diffusion coefficient. This we had done in detail in the beginning of Fundamentals of Transport Processes 1, where we had looked at diffusion processes in great detail. So, this is the mechanism that results in diffusion due to molecular diffusion in a gas. In a liquid, of course, instead of the mean free path, you will have a molecular length scale, a molecular diameter. Okay. However, in the case of turbulent diffusion, in addition to this, you also have diffusion due to turbulent eddies. Okay. And that diffusion due to turbulent eddies, the turbulent diffusion, is proportional to the length scale of an eddy, the spatial extent of an eddy, times the velocity fluctuation of an eddy itself. Okay. Turns out that this is much larger than the molecular diffusion coefficient in a turbulent flow. And for that reason, turbulent flows are highly diffusive. The diffusion coefficient is much larger than the molecular diffusion. And associated with high diffusion is also high dissipation. Okay. The shear stress at the surface is represents the flux of momentum perpendicular to the surface. Okay. That is balanced by the pressure gradient at the 2 ends in the case of an internal flow. The flux of momentum, if it were just molecular, would be just given by the viscosity times the gradient of the velocity. Okay. However, you have this additional mechanism of transporting momentum across the flow due to turbulent diffusion. So, that turbulent diffusion is much larger than the molecular diffusion. So, therefore, the momentum flux from the surface in a turbulent flow is much larger than what you would expect for a laminar flow, okay, of that same average velocity. Because of that, the wall shear stress also is large, and therefore, the pressure difference that is required is also much larger than that for the laminar flow. That much higher pressure difference also results in a much higher friction coefficient in a turbulent flow. So, that is the reason that the friction coefficient you see is at the transition point, there is a jump from the laminar friction coefficient or the friction factor to the turbulent friction factor, which is much higher than 16 by Re. So, of course, if you have a highly irregular velocity profile, it is difficult to model the velocity profile, because we usually assume that quantities are very smooth in space. Okay. So, how do we model a turbulent flow? Okay. A simplistic approach would be to say that we do not worry too much about the fluctuations themselves, but let us just try to write down equations for the mean velocity profile. Okay. So, let us look definitely at one particular configuration. Okay. Let us just take, for example, make a reference to a simple pipe flow. Okay. Let us take a steady state velocity profile, so that there is no time derivative in the conservation equation. Okay. I know that locally at each point the velocity is fluctuating rapidly. Okay. However, on average, if I average it out over some period of time, the mean velocity is independent of time. Okay. You get a mean velocity that is independent of time if you average it over some period of time. In this particular case, the flow is only in the x direction. So, the mean velocity is only in the x direction, there is no mean velocity in the y and z directions. Okay. So, simplistically I could say that I want to separate out the total fluid velocity into this, into a mean capital Ui plus a fluctuating part Ui prime. Okay. The mean velocity I will define as an average over time. Okay. In this particular case, I am considering the flow that is statistically steady. Even though there are local time fluctuations in the velocity, if you average over long periods of time, all quantities have averages which are independent of the time period over which you average over, provided it is sufficiently large. Okay. So, I define capital Ui. Okay. Okay. This is how I define the average velocity. So, I have some time period t, okay, and I plot the local fluid velocity at some location. I plot the local fluid velocity at some location, one particular component of that fluid velocity. It is a fluctuating value, okay, it shows fluctuations. Okay. If I take integral 0 to capital T dt of Ui, I get the total area under this curve. And that is equal to capital Ui times T, okay, where capital Ui will turn out to be the average velocity. So, this is the average velocity times T times capital T is equal to integral of the velocity over time. Okay. As I said, in the y and z directions, this velocity will be this average velocity will be equal to 0, because there is no net motion in the y and z directions. However, I can write it in this fashion, okay, and then if I do it this way, okay, then I get Ui prime is equal to Ui minus Ui. If I take the average, okay, so I will also write this average as Ui, okay, I will use this symbol for the average. If I take the average of Ui prime, okay, if I take the average of Ui prime, okay, is equal to 1 over t integral 0 to t dt of Ui prime is equal to small ui minus capital Ui. Okay. Note that capital Ui is independent of time, it is already a time average. Small u, which is the fluid velocity, does of course depend upon time, okay, but capital U is the average velocity which is independent of time. Okay. So, I am basically integrating a constant capital Ui from 0 to t and then dividing throughout by t. Okay. So, this just becomes equal to 1 over t integral 0 to t dt Ui minus the velocity capital Ui itself. Okay. Because capital U is independent of time. Okay. And of course, I know from this relation, okay, I know from this relation that capital Ui is equal to 1 over t integral 0 to t dt of Ui. So, this means that the average of the fluctuation has to be equal to 0. Okay. So, the average of Ui prime has to be equal to 0. So, I can separate out the velocity into a mean part plus a fluctuating part. You do the same thing for the pressure. You do the same thing for the pressure, separate onto a mean part and a fluctuating part. In this particular case, I have a steady state flow, and therefore, I can separate out the separate out the integration over time with the spatial differentiation that I will do in the conservation equations. If you had something that was time varying, that would be much harder. In that case, you would have to do what are called ensemble averages. In this particular case, since I am focusing only on a steady state flow, I can do this averaging explicitly. Okay. So, what I will do next is to take this separation into capital U and ui prime, insert it into the momentum conservation equation and try to see if I can get some closed form equation for the momentum conservation equation for the mean velocity alone. Okay. So, if I can do that, then I can solve for the turbulent flow mean velocity alone without worrying about the turbulent fluctuations. As we will see in the next lecture, you cannot do that quite so simply, and we will look at the reasons for that and continue our discussion on turbulent flows in the next lecture. We will see you then.